opportunity for this exciting event to share some of our works happening in our institute. So we are working on developing some kind of diagnostic tools which can be used for the detection of oral tumors. So I'll share some of the stories related to that. To start with some of the recent cancer statistics about cancer, globally if you look, it's one of every 6 deaths is caused by cancer. Especially in India, if you look, it is the second most cause of death, followed by after cardiovascular diseases, and the most common kind of tumors which accounts for 50% incidence is oral, breast, lung, cervical, and stomach cancers. Now, coming to the recent incidents, like in the last year, if you look, the major hit point is caused by the breast cancers, followed by oral cavity cancers. So far, till date, whatever all the studies are reporting the importance of, or the emphasis of early diagnosis, which is highly correlated to the 5-year survival rate. So in an early stage, if it is diagnosed, the patient has got a 5-year survival rate around 90 to 100% without any kind of phenotypic difference. But if it is diagnosed in a late stage, it has come down abruptly to 20 to 30%. So in this context, there is a prime importance or a huge demand where we need to have some kind of a novel diagnostic tool to be kind of developed. So the current scenario, if you look, there are different types of tools available in clinical settings, like the imaging-based PET, CT, MRI, ultrasound, endoscopy tools, biomarker analysis, genetic analysis, the mutation analysis, and the histopathology standards like the biopsy. All sorts of information can be obtained. But if you look the total roadmap for the diagnosis, when a patient comes to the clinic and the time he gets the reports in his hand, it may take few hours to several days. So can we come up with some kind of a solution for that? Whether some devices, we can provide some information in few minutes. So that is the questions we asked, whether we can develop a rapid, real-time, accurate, minimally invasive, label-free diagnostic tool that can detect malignant transformation. Something like this, in an OPD situation, when a patient comes, directly the clinician can get the information, or in the surgical scenario, to detect the margins, or in a community level screening, we can take a portable device and go to the rural areas and screen the patients. So keeping these objectives, if you look, there are quite a lot of works happening, like already the previous speaker has mentioned about the optical imaging based methods. So if you look the overall scenario, these are the major works happening around the globe, like developing diffuse reflectance Raman spectroscopy, fluorescent spectroscopy, and Raman spectroscopy based methods have been tested. But overall, if you look, by looking at the chart, you can see the spectral information carried in Raman spectroscopy device is much, much higher than any other methods, because the number of molecules contributing for such kind of a spectrum is very enormous compared to other fluorescent based methods. So just brushing up some of the basic physics, just to know what exactly is that. So already we have studied in our school days, like the Raman effect. The eminent Indian scientist, we got the Nobel Award based for his invention. So whenever light falls on a molecule, what happens is different types of processes are happening, scattering, absorption. So some of the photons scattered carry some kind of energy difference compared to the incident photons. This is nothing but it is reflected by it is proportional to the energy, vibrational energies, basically the bonds. So you can see the different kind of vibrational modes happening here. But the problem with this technology is that it is very feeble. The signal is very feeble. Only 1 in 10 million photons show a Raman effect. All others will be having a kind of elastic scattering. There will not be any energy difference. So what we can do with that? With the emergence of nanotechnology, this has been solved. If we have a metallic surface, rough and metallic surface, and when we place the molecule over the surface, what happens is the signal is getting enhanced several folds. 10 times it is getting enhanced. So we are going to use this kind of a technology for our further studies. And the major advantage is that the components involved in this kind of an instrumentation, whenever there was a discussion, the cost factor, it is very minimal. Whatever we require is a laser source, an optical fiber to carry the light path, the spectrometer, and a computer. The advantage is that, again, a microscopy model can be again converted so that it can be directly illuminated onto the patient side. And it can be also made portable device. So commercially, if you look, there are quite a lot of portable devices available in market, but most of the devices are make use in material industry, analyzing the material samples. We don't have the kind of capability currently achieved to enter in the biological frame. So what are the major results? For example, again, if you look at the scenario, like the concept has not been tested recently. It has been kind of tested very long back, starting from the 90s. But these are the kind of actual number of publications available in PubMed when you search for Raman spectroscopy and cancer diagnosis. But so far, we have not witnessed any of a successful translation. What are the reasons for that? So the major reasons are the biological scattering cross-section is very weak. What we can do for that? Tissue autofluorescence. Once there is a fluorescence in the tissue, then the Raman signals will be masked. And the third aspect is the complexity in data analysis. The spectrum is always kind of complex, even in different tissue types. So the solution is we are introducing SIRS. The signals can be enhanced, the autofluorescence can be quenched. And the third part, I don't need to explain too much, the influence of artificial intelligence, the statistical methods, different types of multivariate analysis tools are already available, which we can clearly differentiate the spectrum. So this is a kind of a spectrum. For the red one, that indicates the spectrum from a tissue. This is basically contributed by a lot of overlap molecules. The relative abundance of different types of molecules in the tissue contributes to the spectrum. For example, like protein spectrum, lipid spectrum, individual amino acids, everything contributes from an overlap tissue spectrum. Now, we cannot expect the presence or absence of a peak for the cancer diagnosis. It will be reflected in different ways. Maybe the peak shift, maybe the broadening, maybe the intensity ratio between the two peaks. All these things are contributing for the diagnostics aspect. So for that, we need to have some kind of a tools like spectral analysis tool. Quickly, I will explain you how exactly it works. I just took different types of spectrum from proteins, BSA, HSA, casein, milk protein, and transferrin. If you look, BSA, HSA are the kind of model proteins, no big difference, only a tryptophan molecule. But when you come to casein, two major differences are there. When you go for transferrin, again, because of the presence of iron, there are, again, 4 new types of peaks are generated. Altogether, the basic platform is same, but there are minor changes. Now, with the help of these algorithms, what we are trying to do is, we are trying to differentiate, based on these minor variations, we are trying to differentiate these types of spectrum. The BSJS, SHA is kind of clustered, transferrin is again kind of clustered, and casein is again clustered based on the significant difference in the peaks. Now, we have solved that issue. Now we have to have some kind of a substrate which can enhance the tissue signals. For that, we apply different type of template methods. Titanium dioxide-based nanostructures of different shapes has been generated, followed by its deposition of silver nanoparticles onto the surface. Further, tissues will be taken on the surface, and the spectrums will be generated. So these are some of the characterization of different substrates we developed. The scanning electron microscope image, before and after silver nanoparticle deposition, you can see the particle deposited there. And we tested the efficiencies of the substrate. The leafy pattern showed a very high enhancement compared to all other substrates. And in fact, we could detect the kind of a standard dye molecule at a concentration of 10 power 9 molar. That is nanomolar concentration of a solution we could detect. Further, we framed it to a kind of a catheter, kind of a device model where the tissues can be directly taken and can be observed under the microscope. So this is a typical representation of the signatures from oral and tumor, normal and tumor tissue. All the major characteristics, group frequencies and fingerprint frequencies are available there, where all the protein, lipid, DNA, collagen fibers are there. So quickly, I'm going to the results. Now we collected the data from different patients, and this is the chart. You can see all the normal categories kind of completely differentiated from malignant squamous and verrucous carcinoma and against pre-malignant lesions. And we further again, there is a cross-validation method. People working in the statistical methods know that, like, there is a cross-validation method, whether the system will take out one spectrum out and look for whether all these features are obeyed in that, the total features are obeyed. So based on that, we achieved a 97% accuracy in this kind of a classification. The real use is that, for example, whenever we develop a kind of a validated set of database, you can use the unknown with the patient data as kind of a prediction model. You can predict the spectrum where it actually falls. That is a real application. And further, I'm quickly moving on. We need to check the sensitivity, whether the grading can be differentiated. So we again looked for different types of gradings, well differentiated, poorly differentiated, moderately differentiated spectrums were taken. Again, you can see this is very well differentiated. Further and quickly moving, we again, quite a lot of things we have done. Okay, we worked with the different phospholipid variations, whether this can be detected. and using our device, we could detect with an accuracy of 84% the phospholipid variation happening within tissues are also got diagnosed. The major challenge is actually how we can convert a microscopy model to a portable device. So we are, for the last 2.5 years, we are exclusively working, a lot of things are happening. We are developing our own fibers where the sensitivity is very high, the collection efficiency is very high compared to the commercial props right now available. So we have defined each of the fiber aligned itself is kind of very well studied, and further, we are developing a kind of a use and throw kind of a device, a CRS cap onto the surface of these fibers, and further, at ex vivo level, at the tissue section level, we have worked out and we got an accuracy of 91% in differentiating different normal and tumor tissues. Right now, we are waiting for the ethical clearance for the patient testing, direct patient testing. So this is the final device. We have the commercial probe as well as the customized probe we have developed so far. So this technology has already been licensed to a startup company, our own spin-off, Lexmatra Innovations, which is basically incubated in CCAM Bangalore for further trials. And also, there was a kind of some interesting things happening at CTC level. So the key fundamental thing is we can differentiate cell phenotypes. The single cell phenotypes can be differentiated based on their inherent Raman signatures. These are actually the different types of cells, different types of cancer cells versus normal cells. And you can see the right side plot, that is nothing but basically characterizing immune cells. Whenever a DC cell or whenever a macrophage is getting activated, what is happening to the inherent Raman signature? Based on this Raman signature, there is a significant spectral reference that can be again mapped.
Doctor,
So,
we are running short of time, please.
Yeah, fine. Yeah. So with this, I'm just concluding. Thanks to my team, and thanks to the organizing team for giving this opportunity. Thank you.